So in our previous lectures, we have studied some of the important terms that were used, that we have said the potential was one of the important terms that we have used. Then we have the sign conventions. We said that we can go for the sign convention where to take the positive from negative. We can take from higher potential to lower potential, the current is flowing, or for at the node the current, if the inward current is going and outward current is coming at this way. If the inward current is there, it is positive, that is I1 plus I2. That means I1 direction is this one, that is going inward, so we said it is a positive, and whatever the count it is going outward, it is negative. So it was the conventions that we have taken. Then we have differentiated what's the difference between the power, energy, and the work done. This we have this we have covered. Then we have studied the network elements. There the different elements and different classifications were there. That was unilateral. Then we studied bilateral, linear circuit, non-linear circuit. Then we have studied what is active elements. Then we have studied passive elements. We have studied what is lumped parameters and distributed parameter. So after that we have studied what is importance of resistance. In that we have studied the resistivity. We have studied what is current. We have defined the current. Then we have studied what are the different sources available, different sources. That was AC and the DC. We have defined that it is AC or it is the DC, and in AC we have frequency 50 Hertz. In the DC we have the frequency 0 Hertz. We have studied what is the importance of 1 upon T. Then coming forward, we have studied in the sources we have dependent and independent sources. In the dependent sources we have studied the four type of the sources are there: voltage, current, and current, voltage, current, and voltage. That is the dependent sources. It is voltage dependent current source. Then we have the current dependent voltage source, then the current dependent current source, voltage dependent voltage source. Then after that we have studied we have done some numerical, like on what power absorbed and supplied. We have done some numerical. Then we have studied some of the tools. I have said that there are some of the tools which are used to minimize the circuit, and to make it simple. We use these in this. The first thing was the source transformation was there. Source transformation. In this we have said that the voltage can be converted to the current source, and the current source can be converted to the voltage source. So these are the tools that we have studied earlier. Now moving forward, we have one numerical here. So we have to study what is the potential difference between the X and Y in the network shown. As we can see in the network, we have the positive terminal. First of all, whenever we are going to solve the circuit, we have to give the sign conventions, and it should be taken properly. So in this circuit, we can say it is a positive and the negative terminal. So the current will be flowing like this in this circuit. It will be going like this. Now we have the second loop. The current direction will be something like this, that the current will be flowing from I2. If I say it I2, it will be flowing like this, and it will be coming like this. So if according to the KVL, that is a V1 plus V2 plus V3, we can say that is equal to the summation of all the voltage should be equal to the 0. So it is asking me to find the potential across these terminals. So I need to find the potential across X and Y. So it is a circuit. This is the V. We can assume it V1, we can assume it V2, and we will assume it V3. So from the first loop, what we are going to take, we need to find out the value of the current. So if I go for this, I will write some equation. Just get sure about that. That is, I said that this will be the 3i1 plus of 2 of i1 or minus of 2 is equal to 0. I can write this also. So why? Because I said that the negative, it is entering into the negative. So I have taken it is coming from the positive, so I have taken the positive. So the I1 value was 0.4 ampere. Now coming in the second loop, we can see it is going from this word and coming to this. We can write it as 3 of I2 plus of 5 of I2, or minus of 4 is equal to 0. So 5 plus 3, 8, I2 is equal to 4. So I2 is equal to 1 by 2, that is 0.5 ampere. Now we need to find out the voltage across X and Y. This is the X terminal, this is the Y terminal we are having at this point. So we need to find, we will go like this, and we will be calculating the voltage across the terminal X and Y. It will be something like this. This is the total V that is going to. So we will write Vxy will be equal to V of X of Y will be equal to 3 VAB minus of VBI, and I1 and I2 has been calculated, and we can find out the value, that is 4.7 volt. So the direction of the current is important, because we said that the current direction of the current will be something like this, and it will be going like this, and then it is going like this. We have taken the convention that from it is going from the positive, negative to positive, it is going everything. So it is, so we can solve this by using this equation. Now moving forward, we have network reduction technique in the parallel connection and the series connection. We know in the parallel connection we have the network reduction, that in the parallel, when we are going for the parallel, the voltage difference is there, but the current remains same. No, I'm going wrong. I'm saying that in the parallel the current differentiation is there, that is I, then the voltage in parallel remains same, that is this will be equal. If it is V, then it will be equal to V1, this will be V2, and this will be the Vn. So it will be equal, V1 will be equal to V is equal to V2, and V is equal to Vn. So this is the property of the parallel. So how we are going to solve it? We can solve it by the current differentiation. We will see some potential is there, some potential, other potential is there, another potential is there, because of the resistance value. So coming to the inductive circuit, it is similar like the resistance connected in the series circuit. It is similar like that. This will be the L equivalent will be calculated L1 plus L2 plus N. If it is connected in the parallel, it will equal to the L equivalent will be calculated like this, 1 upon L. Now we have the ideal voltage source. Four conditions are there. What we are doing, this have been solved by using the source transformation. Source transformation example is this. What is this? This was the ideal voltage source. This means the internal resistance Ri value is equal to 0. That the internal resistance is not taken. So if two voltage sources are connected in the series, this will be equal to V1 plus V2. But when we are going for the practical source, we have internal resistance, that is R1 and R2 across the voltage V1 and V2. So the equivalent will be the sum of the equivalent resistance and the sum of the voltage across this. Then we have the practical voltage source connected in the parallel. This was connected in this series. Now we are connected in the parallel, so we have the internal resistance R1 and R2. This is V1 and V2. So by using this, we have transformed the voltage into the current. Current transformation is there, and the I2 is calculated like this, and R2 is calculated like this. The I1 is calculated. This is the I1, and this is the I2 value. This is I1 and this is I2. So we have transformed it, I1 plus I2, the two are connected in the parallel, it will be equal to I1 plus I2, whereas the resistance, equivalent resistance, these two are connected in the parallel, so it will be like this. So the equivalent can be drawn like this. Now when we are going for the practical connected in the series, these two are connected in series, we can convert into a voltage source, that is V2 can be equal to I2 R2 connected in the series this way. So the total resistance, these two are connected in series, the total resistance is R1 plus R2, and the voltage is V1 plus V2, and we can again transform it into the This is the voltage source. What we can transform it, we can transform it to the current source. What we did, we have transformed this current to voltage first, and then when the voltage transformation is there, we are converting into the current source again, and I is equal to V by R. This is the resistance that will be connected in the parallel. So this is how the practical voltage sources are connected. Now we have another tool that is known as the voltage division rule. This we can say that if we are having the total voltage is there, V and V1 and V2 are the two voltage sources that are connected, having the resistance R1 and R2, and the current remains the same. As we said that in series, the current remains the same. So I will be equal to V upon R1 plus R2. So the V1 will be equal to I1 R1. By taking this value, we will calculate that the Vn will be equal to the voltage. If we are calculating any voltage across this can be 1, 2 or 3, then we will be equal to the total resistance connected to the system and the Rn, that is the third. If we are calculated V3, if we need to calculate if some resistance is connected there, or V2 we are calculating, then this will be equal to R2. This is the voltage division rule. That we need to understand that by seeing the circuit we can transform it, like we said, the voltage can be converted to current and current to the voltage. Now we have the current division rule. In the current division rule, what we are saying, these two are connected in parallel. Now when these are connected in the parallel, the voltage remains the same in the parallel, but the current is different. So the current distribution is there. That is, I is converted into I1 plus I2, I1 and I2. That is having the voltage. We have the resistance R1 and R2, and the combination is V1 and V2. We can say it. So the V is equal to the V1 and V2. That means V is equal to V1 and V1 is equal to V2, but the current remains is different. So what we said, we have calculated the R equivalent, that will be V upon I, that is R1 R2 upon R1 plus R2. That is these two are connected in the parallel combination. So I is equal to V upon R equivalent, we can calculate. So the I2 will be equal to V2 upon R2, and if we calculate this, we can say that the R1 will cancel this is equal to V1 upon R2 only. So I2 will be equal to the total current that is going to the circuit, that is entering current, into the R1. We are calculating the current R2. I2 we are calculating, and the resistance we are taking R1. So this is the current division rule that we have solving that. This is also the tool that we use. Now we have the third tool, that is the conversion from delta to star and star to delta. These are the we have to study delta to star and star to delta. These are the two transformation, and we have the derivation for this, and that is very simple. I will take one example. That, for example, if I have this resistance source, that is R1, and we have other resistance source, that is R3, and we have other resistance source, that is R2. So if we need to calculate, we are transforming the delta to the star. That means we are going to transform it into like this. This will be this will become like this. So the delta has been transformed into the star. It will be the equivalent will be like something like this. And this will be, we can take and give it any name, R12. That means, and we can give it R13, and we can give it R23. It's my wish. I have given this name. So now what we are saying in the derivation, what I said, if we are going for the delta to star, we have, if we see this circuit and we need to find out the RBC, that means we are calculating R and BC across this. So we can see that the R3 BN across the B and C, this is R3, but if R1 is, this is connected at R1 and this is connected R2, this is R1 and this is R2. So these two are in series and this is in parallel. So we can write that, we can write RBC is equal to it is the RB plus RC. We can write this also. So it is equal to that means R R1 plus R2, because these two are in series, and it is in parallel with the R3. So if we are going for this, we will have this equation, that is R3 R1 plus R2 upon R3 plus R1 plus R3. That's the equivalent circuit. That is for the RBC. Similarly, we can calculate it for the for RCA. we can calculate it for our AB. Now third, fourth and fifth equation, what we are doing, we are adding the third, fourth and fifth equation. So it will be the twice of RA, RB and RC with the twice of this value from equation third. So RA plus RB plus RC is equal to, we have calculated the sixth equation. Put the value of RB plus RC from equation third in sixth, from third and the sixth, this value. When we are going to put it, then we can calculate the value for RA, that is comes out to be the R1 R2 upon R1 plus R2 plus R3. That means we have calculated RA, this rather than R12, we have said it is equal to RA, and this is RB, and this is RC. So this is how, this is the derivation that we have. But I will tell you the another way of solving it. Rather than going for the such a long derivation, we should know the derivation also, how we are performing it. But the simplest way to the delta to star transformation is simple, one trick also there to make it remember, because while solving the numerical, we are not going for such a long derivation. So what we are going to do here, we are taking one example rather than this. I will take this one. What we have one delta transform that we have, like this one. This is, we said this is R1 as it was given. This is R3 and this is R2. And we have transformed it into, the RA that was given like this. This was said to be RA, and the other, it was said to be the RB, and this was said to be the RC. So if it is going to be asked me what is RA across, if it is a delta. So remember this, when we are going from the delta to star, we have to check which two branches are connected with RA. This is R1 and R2 are connected. R1 into R2 plus the total resistance, that is R1 plus R2 plus R3, that will be common for everyone. For example, if I need to find the between RB, if we check about RB, we have the two branches that is connected, that is R1 and R3. So RB will equal to R1 into R3 divided by R1 plus R2 plus R3. Similarly, we have RC. If we are going for the RC, we see that the two resistance that is connected is R2 and R3. So it will be R2 R3 divided by R1 plus R2 plus R3. This is the simple way to remember this. We have to just remember which two branches are connected with each other. This was the transformation that we go for the delta to star transformation. This is the derivation, and then we have this, what we have said. This is a trick that we use to calculate it rather than going for the such a from derivation. Now we are going to see the second one, that is the star to delta transformation. Then if we see this one, we have calculated the value. This, now we are going to for the star to delta transformation, then now we are going to transform this into, this will become R1, and this will become R2, and this will become R3. So that means earlier we have done delta to star, now we are going from the star to delta. What we are going to do, we have taken that the same conditions that we have. So to remember this, we need to go for one numerical, we will go for it. So in this we can see that the R1 that we have calculated, where it is written divided by 4, that is RA. Coming to the numerical, one of the numerical we are going to solve it. We have this numerical and it was asked to calculate the total resistance across the terminal A and B. A and B is this one. Now we have to see which is star, which is delta. We can see that this point, if I go for A, B and C, this is something like this: 5, 20 and 50. So we are going to transform it into the delta to star. What we will have the second figure we can see this. In the second figure you can visualize it. What we have, we need to find out the value of the terminal, that is R1, R2 and R3. So as I told you that to calculate it, first we need to find R1 will be calculated. I said the two branches that are connected with the R1 terminal, that is 5 into 20 divided by the total resistance across the terminal, that is 5 plus 20 plus R3, that is 15. This is the value of R1. Similarly, we can go for R2. That will be R2. R2 is this, and the two branches that are connected is, that is 20 and 15. So it will be 20 into 15 divided by 20 plus 15 plus, that is left with the 5. Similarly, we have R3. R3 can be calculated. R3, where is this? R3. R3 is connected with the 5 and 15. So it will be 5 into 15 divided by the total resistance that we have, 20 plus 5 plus 15. So this is R1, R2 and R3 has been calculated. So now we have calculated R1, R2 and R3, the values we will calculate, and by this we will have the another transformation. Now we have the other transformation. What we have 12.53. Let me show you how we calculated. Here you can see it, how we have calculated, that is R1. We said that the R1 will be the two, with the R1 with the two, that is two branches that is connected, 20 into 5. These was the 20, this was the 5, and this is the equivalent resistance. We have calculated 2.5 ohm. Then we have calculated R2, that is 20 into 15, 7.5. Then we have calculated R3, that is 1.875. So these were the, now this 10 and 2. Now we have the circuit. We have the circuit like this. This was the 10. This we have calculated, that comes out to be the, we said that it is a star. So in the star, when we have formed it, the value was R1, and the value here it was R2, and the value that we have here, this was R2 and this was R3, and this R3 is connected with a 2 ohm resistance here, and this R2 is connected with a 30 ohm resistance here, that is this one, 30 ohm resistance is there, and that is connected at this point, coming at this point, and we have the 30 ohm resistance still here, and this was the point B we have obtained. So in this we have 10 and 15, and this 10 is connected with a 15 ohm resistance still, and that is connected at this point. So this is the equivalent circuit. This R1, R2 and R3 we have obtained. The R1 value will be, it will be coming in the series. R1 was 2.5, so it will be 12.5. This will be 37.5, and third one will be 3.875, because it was 2 and R3 was equal to 1.875. So we have the value, that is 1.875. Then R1 was equal to 2.5, and then the R2 we have 7.5. So these two are connected in series, this one and these two are connected in series, this one and this two is connected in series, and this one and this two is connected in series. So we are left with 15 ohm that were already, then we have 30 ohm, this is connected here. Now we have obtained this. Now we can see this again, it is a delta transformation, it is forming a delta. So we need to convert it into the R4, R5 and R6. So the R4, R5 and R6, we need to find the values, that is R4, R5 and R6. So how we are going to do this? Same again, the process we will follow. We will say that the branches that are connected, we can directly calculate it. It will be like this. If we go for the R4, I5 and R6, then we are going for the R4. If we are going for the R4, we are going for this R4. Let me change the color so that it will be easily available. So we can see this R4. This is R4. This R4 is connected with the two circuit, that is this and this. So it will be 3.875 into 37.5 divided by the total resistance. Then we can similarly calculate R5, that is R5, 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 R5. This is connected with the two branches, that is 30 and 37.5. that is 13 to 37.5. Similarly, R6 can be calculated. This was the R6. So we have these two will again come into the series. We have 15.76, that is 14.54, 15 and 1.63. This 15 is left still here. So the equivalent resistance will be like this now, and these two are connected in series. So 15 plus 1.63 is in parallel with 14. We will see that 15 plus 1.63 is in parallel with 14.54, and this all is connected in series with the 15.76. So this is the equivalent resistance that we can calculate. So this is the equivalent circuit. We have calculated the value, that is 23.5. Now coming to the other part, that is we have the loop. We have studied what is the loop earlier, also nodal method. Now we are going for the loop and the nodal method. What is a node? We said that the node of the network is equipotential surface at which two or more circuit elements are joined. In this, we can say a junction is a point in an electric circuit where three or more elements are joined. This is two or more circuit elements. This is three or more circuit elements are joined. This is known as the junction. So we can say that the junction is always a node, but a node may or may not be the junction. We will see this by the numerical. We will use the numerical to understand this, how we are saying it, what is a junction, what is a node, what's the difference between them. Then we have other thing, that is a loop and the mesh. It is said that the loop is any closed path of the electric network. A magnet mesh is most elementary form of the form, and it cannot be further subdivided. This is the important. This cannot be further divided into another loop. For this also we will have some numerical to understand that how what's the difference between the loop and the mesh. So we can say that the mesh is always a loop, but a loop may or may not be a mesh because it cannot be further subdivided. So to go for this, we have one numerical here. In the numerical, we have taken the circuit, that is this is R1, this is R2, this is R6, R4, R5 and R6. This is connected with a voltage source, that is V. So first of all, we need to find out the branch, how many branches are there. And if you see this, with the total of the branches represented by B, the total number of the nodes are represented by N, and total number of the junction is represented by J, and the total number of the mesh can be calculated by using this equation. So we are going to calculate. First of all, we need to find the branch. So the branch is that which is having some element in it. So this is we have V, R1, R2, R3, I5, and we have total R5. So we have total branches are there, seven branches are there. Now we need to find out the junctions. Junction was said, if we find out the junction, it is first junction because it is connecting the two elements, this 3, 4, 5 and 6. We have total junction, we have 6. So if we need to find out the mesh, we need to find out the how many mesh there will be there. So the mesh can be calculated. Number of the branches, we said number of the branches are 7, and number of the junction is 6, minus of 1, that is 7, minus 5, that is 2. That means the number of the mesh can be calculated as 2. This cannot be further, as in the definition we said that which cannot be further differentiated or subdivided. So this cannot be further divided because it is not having. So we have the two mesh, that is 1 and 2. Now we are going to calculate number of the loops. So the loops can be calculated by L is equal to B minus of N plus 1, that N represent the node. Now we need to find out the node. So if I take this circuit, and I redraw it so that it can be easily understood. If this is the circuit, what I said, it was the circuit, and this was the circuit. We said this is the circuit which is having the voltage source V. Then we said that this was the R1, and then we said this was R3, and this R3 is connected with a term, that is terminal, that is R4. Now coming back, sorry, we have R2, and then we have here we have R5, and this we have R6. We have R6, and this was the voltage. So now coming at the node point, I will call it as a node 1, I will call it as a node 2, I will call it as a node 3, I will call it as a node 4, and I will call it as a node 5. I'm not taking as a node because we said that the potential should be there. So if we talked R3 plus R4, if it is coming the parallel, we are not taking the node because the current is going to remain same in this because there is a no drop. So the number of the nodes that we have right now is 5. So we can calculate the L, that is the number of the loop can be calculated, number of the branches. We have 7 branches, then we have number of the node, that was 5 plus 1. So it will be approximately how much? 8, 5, 6, 3. Number of the loops will be 3. Now we can see the loop 1, loop 2 and the third one, that is loop 3. Loop 1, loop 2 and loop 2 and loop 3. Where is the loop 2? Loop 2 is dependent on loop 2 is dependent on loop 1 and loop 2. Sorry, 3. This was the loop 3. We have this one, loop 3, this one, loop 3, L3. So this is dependent, and if we consider this only, this will be equal to V1. So this is the node concept, and then coming to this numerical, here we can see we have to find out the current through AB branch, that is IAB. We have IAB at this point. This is A and B. This is we need to find the current across this terminal and the voltage CG, C and G, and the voltage across this terminal. We need to find out the voltage across this and the current across this. So now how we are going to do that? First of all, we will define the loop. We have the 2 loops, that is loop 1, loop 2, and this is the loop 3. We have the 3 loops. That means if I consider, first of all, I said that whenever we are going to solve this, we will have the current distribution. The current distribution plays an important role. Current distribution. Now the current distribution will be something like that. For example, if I take this as a I was the total current that was going to flow. So if this was I and I said this will be equal, I said it is I3, and I said what? This is the I1. So I can say this will be equal to how much? This, the current flowing, this will be I minus of I3. I can write this I minus of I3 is the current that is flowing across this terminal. Now what happened? I3 came at this point. This is I3. I said it is I minus of I3. It was going there. Now coming at this point, I said, for example, this was the current that is flowing, that was I2. This was the current I2. So the current flowing at this terminal will be I minus of I3 minus of I2. And after coming at this point, it will be I3 came again, then it will become I minus of I2 again. It will go from this circuit, and at this point it will again come with the I2, and the current is I. At this terminal we said that it is this at this point. What happened? Here the current was I minus of I2, and the current across this terminal came with this I was equal to I minus of I2 or plus of I2, because the current entered at this point. So the current that we taken, that was I, and at the output also the current, incoming current, the incoming current is coming again to be I. That means this is the current distribution that we did. This was the one way when we are going for the current distribution. Other thing what I can do, this was the current distribution. Now if I change this, I make it like simple. This was the current distribution. That means the current can be distributed like this. And now what we are going to take, we said that we have the 3 loops. We have the 3 loops. That was the first loop was this, the current is flowing in the circuit like this. This is the current. This is the second loop. What we said this is the second loop. In this the current is flowing in this direction. That means at this point the current I1 is going this side, and in this side I2 is going this side. So the current in this will be equal to I1 minus of I2 if we are going for this circuit, first loop. And for the second loop it will be I2 minus of I1. For the first loop, that is loop 1, and for this loop 2, this will be I2 minus of I1. So if now we have I3, and this we said that this is the current that is flowing into the circuit, that is I3. So that means in R2, across R2, if I need to find out the current across R2, this was the current I1, and this the again current was coming at this point is I3. So when we are taking the loop, the current across R2 will be I1 minus of I3. Similarly, if I say the current across the terminal R3 will be, the current across the terminal R3 will be like the current in this, it is coming I3 at this point, it is coming I3, and at this point R1, R4. If we calculate R4, the current will be depending upon I1 minus, if we are taking the loop 1, I1 minus of I2, and if I are taking the second loop, then it will be I2 minus of I1. So this is the drop, this is the current distribution again, this is the another way of solving it. Now what I did, I said this is another way that the current, incoming current, we have calculated. So now we are going to calculate what is the voltage, what is the current that it was asked. So for that we will form a loop. We will take one, I will take one loop from this and the another loop like this, and then we are going to solve for it. So if I take, for example, if I take this loop, I take this loop as my first loop. So this is positive terminal, this is negative terminal. What I'm going to do, I will start from this point. I said this was the current that was flowing, that was I1, and this was the current that is coming inside it, this is I3. So I will write that R2 I1 minus of I3 coming at this point, we have came to at B point, B4 we have this R4, and the current will be, the current is going this direction, and this the current is, the current that is flowing in this was I1, whereas the current coming from this side is I2. This is I2. So I4 I1 minus of I2, then coming at this point we have, this is equal to minus of 3 volt. So the first equation that we have obtained, that is R2 I1 minus of I3 plus of R4 I1 minus of I2 is equal to 3 volt. This is the first equation we have drawn from this circuit. Similarly, when we are going for the second equation, what we are going to do, we are going to solve this. Now in this we said this was the R3 that is going. So in this I3 is coming from this point. I3 is coming, and this, and we said that the I2 is flowing from this circuit. So here it is I2. So what I will write, I will say 4 of 4, that was the resistance, the current that was going I2, and the current that came, that was I3 at this terminal. Then again we have V1, that was the voltage that we said V1, it will be V1. Then it is going at this point, and it is going into entering into R4, that is R4 was 2 into the current that was coming. Now we said 2 I2 minus of I1. This is the second equation for the second loop. Similarly, when we are going to solve for the third loop, the current is going to flow like this. So it will be 3 I3, because the resistance to the current coming at this point, then it is entering this side and coming at this side. Then it will be the I3 plus of 4, it will be I3 minus of I2. Then coming at this point, at this we said that it is I3, so it will be 1 ohm into I3 minus of I1. I3 minus of I1, this will be the third equation. So now we have obtained the 3 loops we have taken, and now we have 3 equations, equation number 1, equation number 2, and the equation number 3. So this is how we are going to solve it. So what we said, applying the KVL equation, we have obtained, that is 3 I1 minus of 3 is equal to I1. If we go for that, This was the first equation. After solving it, we will obtain this equation first, we will obtain the second equation this, and we will have the third equation this, and by solving it we can calculate the value of I1, I2 and I3. I2 and I3 will be calculated, and then we have the current distribution that we said, that was I1 minus of I2 was there, and then we have I2 minus of I1 was there, then we have I1 minus of I3 was there, then it was I3 minus of I1 was there. So it can be calculated that I2 minus of I3 will be there. Then this is how the I1, I2 and I3 are calculated. So the current and the voltage we have obtained, this was the value. Moving forward, this was how the KVL equations are written, and this is how they are solved. So coming to the next question, we have this is nodal analysis. This is based on the nodal analysis. That the earlier that we did, that was the loop. By using the loop analysis we have solved this. Now we have the nodal analysis. This is a numerical that we have for the nodal analysis. So first of all, we need to find out, we have to use, by using the nodal analysis, the total number of the equations of the node can be calculated by n is equal to j minus of 1. So now this is the numerical. Now we know the tools that we studied. We said the voltage to current transformation. We know that current to voltage transformation. We know that star to delta transformation is there, and star to delta to star transformation is there. So now by using the nodal analysis, if we are going for the nodal analysis, we said this is the node, first node. Okay, then we have another node at this point, and the third node at this point. How we can say we are saying that is a node? Because I have one option also. I can convert into the current. The current is there, so I can convert into the voltage also. This is also, I can minimize the circuit. I can minimize the circuit like this. I can minimize the circuit like this, because it is asking me find the current I, that is flowing at this terminal, and it is asking me the current across this is the I, using the nodal analysis. So what I can do, this is the current, so that means I need to find the current across this terminal. So if I use a source transformation, it will be 3 times 30, that means this will be the 30 volt connected in series with the resistance, that is 10 ohm. This and this will become like this, it will be the 10. So it is asking me at this terminal the current across this terminal. So I can use the nodal also, but I can use the source transformation. But before going to the source transformation, I am just going to solve it by the nodal analysis. So in the nodal analysis, the first thing that we need to find out what number of the nodes we need to find. This is the node, I said this is the node, and this is the third node. So what I say is said that it is I, so that means we have this current. So the first of all, the current distribution should be in the nodal analysis. We can say that the current that is going, it is going like this, and it can be distributed like this. If I say it is I2, and if I say it I3, and if I say it I1, so the I1 will be equal to I2 plus of I3. Okay, this is one of the sign convention we can say, or we can use this also. We said that we can say if it is I1 and the current is going inward, and this is I2 and this is I3, every current is going inward, that means sum of all the current at this point should be equal to 0. I can take this convention also. That means the current is going in this, the current was entering and it is split into two parts. So I will take this convention. I'm going to take this convention because it is, for me it is simple. So if I see the circuit, let me erase it to show that we can easily understand it. So this is how we are going to transform what I said. Now coming to the loop, KCL equation we are going to use, because the nodal analysis is solved by using the KCL equation, where the loop is solved by using the KVL. So what I said, the current entering, I said this is the 3 ampere was the current that was going, and it was distributed in two parts, that is this and this, and the one is I, another one I need to find. So what I said, it is, for example, it is I1. If I said it is I1, so this was the current. So this will be 3 ampere is going to split into two form, that is this, if I say this is the potential VA, if I'm taking, so it will be VA minus, what is the resistance? No resistance, no voltage sources attached. For example, if there was any voltage that was value was VB, or it was 5 volt, then what I will be writing it as a 5 volt, VA minus of 5. But in this case we don't have any other source connected to the, only the resistance source is there, so it will be VA minus of, it will be VA minus of 0 divided by the resistance that is connected to the circuit, that is 10. Now the current has been, this was the first current that we have said, this was the second current. I can write it simply I also. I can write it I, because this is the current that has been already given. But if I need to find out what I can say, I can write VA minus of 10 is equal to, there is no resistance source, I can say it as a I also. So I can write this and I can write this also. So this was the first equation, that is equal to the, we said that that is equal to the, we can calculate the value. By solving it, we have obtained 10I plus VA is equal to 30. This was the first equation. Now we know that at this terminal, it is VA minus of 10, this point. So I am going to take the node B, because node A and node B. So node B, in this node B, what we are saying? We are saying this was the current. This was the current that came and it was distributed into two parts. This was 6 ampere and in this. So I will write it. I'm going from this word. So we are taking from this word. So it will be VA. If I'm going from this, VA minus of 10. This is the voltage across this, minus of B, that is VB. We will be writing it minus of VB. Let me erase it so that you can easily understand it. This was the first equation. This is clear to you all. This is the first equation that we have. Now we are going to for the second equation. The second equation is like this. I said we are going to calculate from this point, the current is entering and it is split into two parts, that is this and this. So it will be VA, that was VA minus of 10, this is the voltage VA minus of 10, minus of, this was VA minus of 10, that will be equal to minus of VB divided by the resistance that is connected to it, say 60, it is equal to the splitting current, that is VB upon 10, because the entering current is split into 2 point, so VB by 10 plus, we have another current that is 6, that is a 6 volt, 6 ampere, that is the current. So this is the current distribution that we did. So by solving this, we will obtain the second equation, that will be this one. Now coming to the third part. Third part is like this. Now we need, the current has been distributed here. Now at this point, because the current is coming here and it is split into two parts at this point also. It's split into two parts, this green line. So this was equal to how much? It was VA at this point. At this point, when we are going for this, we said at this point it was VA minus of 10, because the direction is taken this way. So VA minus of 10, no resistance was there, so I said VA minus of 10, and it is split into VA minus cut 10 divided by 20. I can say I can say it directly as a I also. I can say I because the I current was flowing. So VA minus of 10, VA minus of 10 plus the current at this point. This was VA minus of 10 minus of VB divided by 60. That was given this. So this was the third equation we have obtained at this. The current that was coming from this point was I. This I was equal to VA minus of 10 divided by 20 at this point, and this was VA minus of 10 minus of VB divided by 60. So this was the third equation. Now we have three equations. That is the third equation we have obtained. That is what the equation's value is given. I is equal to 4 VA by this, and by solving it we have fourth equation. Now substituting the value that I have obtained the value of I. This was the I value that we have calculated, and this I value can be substituted in the first equation. I value has been substituted in the first equation, and by this we will obtain the equation that is 10 VA minus of VB is equal to 2 to 0, and by solving the equation number 2 and 4 in the last 2 and the 4 equation, it can be solved and VA and VB can be calculated. Now coming to the nodal analysis that we have said, the nodal analysis we said in the nodal analysis we will be going for the KCL. The Kirchhoff current rule plays an important role. Identify the number of the nodes when the current is defined. Assign the voltage to the node. Write the KCL equation of the each node and expect a reference node. Write Ohm's law form of the current in the nodal equation and solve the equation. This is a simple step that we have followed. Then we have the mesh analysis, or we said that the loop we will be taking, identify the number of the loops that we said, okay, how we are going to identify the number of the loops, number of the mesh can be calculated, and by this we can solve the circuits. So in this what we do, we have some basic knowledge about the earthing and the neutral, because in our electrical engineering we hear about the earthing is this. If I take, as you all have seen the circuit here, this is known as the earthing point. This earthing is generally used for the protection purpose. If there is some extra source, external voltage, or we can say the internal current is flowing through it, by the earthing it have a very the earth is said to be the zero potential. Earth have the zero potential. So the from higher to lower potential, the all over the voltage of the current get into the this is the earthing. So it is used for the safety and stabilization purpose. Connected to the earth, carries the current only during the fault condition. At zero voltage, the ground potential, to prevent the electric shocks and equipment damage. It is also used for the for example, if we are going for the washing machine or higher instrument circuit, washing machine or higher circuit, it is three terminal devices. Whereas the inverter, we are going inverter. I'm saying that the mobile charger, it have the two terminals. So this is known as the line, and this one is known as the neutral. This is the returning path. We can say neutral is the returning path. So we can say that it is a returning path. Neutral connect to the transformer. The neutral point carries the current under the normal condition, close to 0 volt but not always zero, provide a reference to the system voltage. So simply we can say the earthing is the primary for the safety, connecting the electrical system to the ground to protect against the faults, whereas the neutral is serve as a returning part of the current. So returning part, and it is used for the protection part basically. Now we have another part